Hey friends, welcome back to the channel and to the 12th episode of Research Paper Summary. Today I'll be covering EMNLP 2020 paper, A Simple and Effective Few-Shot NER with Structured Nearest Neighbour Learning. In this paper, they propose a method that combines both nearest neighbour learning and structured decoding to achieve state-of-the-art performance on few-shot NER tasks. In this video, I'll first go over the context and contribution of this paper. I will then dive into the proposed methodology called the STRUCTSHOT. And lastly, I'll finish up this video by showing some of the experimental results and analysis. I hope you find this video useful. Let's get to it. If you're new here, my name is Ryan. I'm a first-year PhD student based in London, and on this channel, I mainly share my personal development journey as a student entrepreneur, covering my PhD research in AI, my entrepreneurship journey, as well as different life design topics. Being the first generation person in my family to pursue higher education and different life and career pathways, I hope that these videos will provide you with some useful information, inspiration, and courage to take more actions and live a happier and more intentional life. If you're a first generation student, entrepreneur, or all of the above, consider subscribing for more informative videos in the future. One of the main challenges for adapting an NER system to a new domain is the mismatch between the different entity types. The annotation for domain-specific entity types can be very expensive since it requires domain knowledge. Few-shot NER classification is the task of classifying new entity classes based only on few labeled examples of each class. There are two reasons why existing few-shot methods does not work well with few-shot NER. The first reason is that NER is a structured learning problem, which means that it's very important to be able to model the dependencies that exist across labels. It's simply not enough to just classify each token independently. The second reason is noisy class prototype. Few-shot classification models typically use prototype-based methods to represent semantic classes. These prototypes are built using the labeled examples in the dataset. The problem with this is that the outside class tag doesn't actually represent any unified semantic meanings. And so what this means is that existing method ended up learning a very noisy prototype representation of the outside class tag. Overall, in this paper, the main contributions are as follows. Firstly, they propose STRUCTSHOT for few-shot NER, where instead of using prototype method to represent each entity class, they represent each token by its contextual representation in the sentence. This makes it possible to build a unified NER system that can identify both existing and emerging types of entities. The second contribution is that they perform in-domain and out-of-domain experiments by measuring the performance of NER model on identifying new types of entities in both the source and various other target domains in one-shot and five-shot settings. STRUCTSHOT is a few-shot NER algorithm that is based on Structured Nearest Neighbour Learning. We use an NER model trained on source domain as token embedders to generate contextualized representation for each tokens. During inference times, these data representations are used for the nearest neighbor token classification. The model also leverages the tag transition between source and target domains and use a vertebyte decoder to capture the label dependencies. Overall, there are two main components to the STRUCTSHOT architecture. First up is the nearest neighbor classification for few-shot NER. This is basically the main component of STRUCTSHOT. During inference time, we are given a test example and end sentences that represents the entity support set. The nearest neighbor classification uses a token embedder to compute the contextual representation for all tokens in the end sentences and compute the similarity score between each token in the test example and all tokens in the support set using the Euclidean distance. The model will then assign each token with a tag that corresponds to the most similar token in the support set. The second component is the pre-trained NER models as token embedders. As mentioned previously, here we use an NER model trained on source domain to learn token level representations. The paper considered two supervised NER models, a bi-LSTM NER and a BERT-based NER model. During inference time, the nearest neighbor classification model will use either the bi-LSTM or the transformer encoders as token embedders before the final linear classification layer. As I mentioned before, in few-shots learning, there's often a mismatch between the tags in the source and the target domain, which means that we aren't able to compute the tag transition scores of the target domain. STRUCTSHOT tackles this problem by using the source domain data to estimate an abstract tag transition distribution. The first thing that I would like to note here is that this formula is used to estimate the abstract transition probabilities. We can estimate the transition probabilities by counting the number of times a particular transition was observed in the source training data. The key idea of STRUCTSHOT is that we can extend these abstract transition probabilities to an arbitrary target domain tag set by evenly distributing the abstract transition probabilities into the corresponding target transitions. For example, the abstract transition probabilities between O and I tag is 0.3 in the source domain. This means that in our target domain tag, the transition probabilities between O and any I tags should also accumulate to 0.3 as shown here. In this paper, we evaluate our future NER systems under two scenarios, the tag set extension and the domain transfer. We do this using 4 NER datasets, the Onto Notes, CONEL 2003, I2B2, and WNUT17, covering a range of domains from general to social media. In the tag set extension, we are trying to evaluate the performance of our model in recognizing new entity types. In the domain transfer scenario, we use Onto Notes, the general domain dataset, as our source domain and test our model on the other 3 datasets covering news, medical, and social media. Here are the results for 1-shot and 5-shot NER. As you can see here, both our NN-shot and STRUCTSHOT outperform previous methods significantly across all evaluation scenarios. By using Vertebi decoder, STRUCTSHOT boosts the performance of NN-shot on 5-shot tag set extension and domain transfer tasks. Overall, STRUCTSHOT achieves state-of-the-art results on the 2 few-shot NER tasks. The result also shows us that BERT-based systems outperform BILSTM-based systems on few-shot NER. This showcases that language model pre-training is important for low-resource NLP tasks. The one thing I would like to point out here, however, is that task-specific knowledge is still shown to be more important than general information learned via unsupervised training. This is shown by our BILSTM-based systems outperforming SimBERT. Lastly, we observed that 1-shot NER systems tend to perform better on domain transfer scenario, whereas our 5-shot NER systems tend to work better on the tag set extension task. In general, domain transfer is more challenging than tag set extension because the language vocabulary can be very different between domains. Overall, our 5-shot NER systems are both more accurate and robust than our 1-shot NER systems. Although the average F1 score for our few-shot NER system is still very low, the paper believes that our system is still very useful in practice. Here's why. Firstly, our few-shot NER systems perform very well if the source and target domain is very closely related to each other. This is shown by our results where our 5-shot NER systems trained on Onto Notes achieve 75% F1 score on the CONEL 2003 dataset. The second reason is that our few-shot NER systems allow us to detect emerging entity types without having to retrain and redeploy our NER models. This is very beneficial because it gives us more time to train a much more accurate NER models after collecting enough supportive examples. And that's it for today's video. If you like this video, be sure to subscribe as I'll be covering more research paper summary in future videos. In the meantime, feel free to check out other videos on my channel. Thank you for watching. I'll see you guys around next time.